Hello, good afternoon, everybody. Let's come back. Now we will start our second poster section. We will begin with the on-site participants, and then we'll give the opportunity for the online participants too. The first name that I will present today will be Dalila Ribeiro, with the poster Progress Toward the Matter Wave Interferometer for Inertial Sensing with Non-Destructive Monitoring of Clock Oscillations. Dalila, please.
Hello. Man, I get so nervous in front of a microphone. So, well, this is my poster. Basically, what we do in the laboratory is we are trying to do a gravimeter that works with a matter wave interferometer. So the technique we want to implement is to put a cold cloud of atoms inside of a ring cavity and monitor the interaction of the atoms with the light and the gravity with the light that leaks out of the cavity, with the transmitted light of the cavity. So there are several technical details in our experiments, and those are in this poster. So we got our article accepted like last week. And so, yeah, that's what I have in the poster. So it's really technical, but if you have more like on the how you say that, techniques that we are trying to implement to measure stuff, I can explain a bit more. But essentially, we have a cloud of atoms oscillating because of a periodic potential in front of a constant force. And this oscillation is already known for many people. It's a block oscillation, and block oscillation, the frequency of the oscillation is proportional to the force. In our case, will be the gravity. So we want to measure the frequency of the oscillations in a non-destructive way while the cloud is still oscillating. Well, I have questions in here. I already answered actually from the one from Bruno. So I'm going to start with Bruno. Why does the number of atoms in the blue mode suddenly decrease after 4 seconds? So that question actually refers to this figure. It's figure 3, so you can see that the number of atoms in the blue mode increase and suddenly decrease. So this was actually a characterization just to calculate the parameters of loading and decay time. So I was loading the atoms in the cloud, and after 4 seconds I turn off the source of atoms. That would be our push beam, so we can then see how the decay of the cloud happens. It's just to measure characteristic parameters. Then in figure 4, I notice a pretty small range of the saturation parameter. Since the red mode is based on a narrow transition, the atomic cloud should fall. Does this happen? If yes, is this part of the process to measure gravity through block oscillations? So, figure 4 will be this one. So it's not pretty small. To be honest, the scale is logarithmic, Bruno. So it's not small, actually. We're oversaturating the transition, and this is like the only way actually to do it, because the saturation parameter of our red mode is like 3 microvats per centimeter square. So you really need like nanovats in a 1 centimeter beam to not saturate or something like that. So it's not a small parameter. So, but at the end of the ramp in the single frequency, we are really close of the saturation limit of not saturating the transition. And what was the other part of the question? Does this happen? Yeah, the red mode, it falls because of the tuning and gravity. Yeah, it happens, yes. Actually, that's the way we use to check if the frequency is correct. To adjust the red mode frequency when it reached the flat behavior, when you see that it's not a circular mode, but it's more like a pancake that is falling from gravity. It's going to be used to measure Bloch oscillation? No, actually no. So our approach is we have the periodic potential and we have the atoms. And we're going to put the atoms inside of the periodic potential. Wait for stabilization, actually, because when you move atoms, you hit up. Maybe also the potential has some irregularities in the bottom. So we first put the atoms in there, wait a bit, and then we measure. So we don't want to move the cloud inside of the potential. No, we just want to see pure effect of the gravity and the periodic potential. It is possible to measure Bloch oscillation with linear cavities. What are the main benefits of using ring cavities instead of linear? Yes, it is possible, yes. It was done already by other people. So I think Hans measured Bloch oscillation with a linear cavity, but they measure it with artificial gravity. So it wasn't, yeah, it was an artificial gravity because they were using rubidium atoms, and rubidium is like sensitive to magnetic fields, so you really have problems by deleting all the forces, all the external forces. So they put a fake gravity. It was just a magnetic field. And is this possible to measure? Yes, because anyhow, the cavity, in the case of a linear cavity, the cavity is just going to create a periodic potential. And it's really easy to create a periodic potential with a linear cavity. You just need one beam, you send it, and it will come back in the same path because the modes are coupled. And yeah, you will have a periodic potential. The deal with a linear cavity is that the phase in a linear cavity is fixed. So if you have interaction of the atoms with the light in the linear cavity, the light the light will show the interaction with the atoms, but is limited to the kappa of the cavity. In our case, we have a ring cavity because we want the phase to be free. So we want to see. We want to send the light in one direction, and we want to receive the information in another direction. So that's the main advantage of the ring cavity. And also, our ring cavity has one of the beams of the ring cavity in the direction of gravity. So far, everybody uses like linear cavities, but they have it like perpendicular to gravity, so it's not so clever to measure gravity. It's more clever to measure something else. As I say, they even use fake gravity for that. So yeah, that's for Bruno. Now Pedro also asked, I have a good amount of I have a good transmission between the red mode and the cavity trap. He wondered if the number would increase, just increasing the blue mode. Yes, Pedro. Yes, my transmission from the blue to the red mode is not that good. Maybe I can still improve parameters, but I have only 4 months of PhD, so I'm going to keep going. next people can improve it. But yeah, if I increase the amount of atoms in the blue mode, it will increase the amount of atoms in the red, and therefore in the cavity. Could you give an example of what collective response you will look for a signature on the presence of atoms in the gravity mode fields? So there are several ways to do this. We already saw the impact of atoms in the cavity light fields. But as I haven't been able to reproduce that, so I cannot assure that. But in principle, what we want to do is so there are several ways to do it, and the easiest way would be to put resonant light with the atoms in one mode of the cavity and put the cavity away from resonance, like we do it, and then scan scan the light in the cavity, and then the light resonance the light resonant with the cavity will experience a mode splitting, because so you have the light inside of the cavity, yeah, and this light that is inside of the cavity is it fits inside of the cavity because of the size of the cavity, yeah, the boundary conditions is for the light to be zero in the borders of the mirrors. If I put atoms inside of the cavity, that means that I change a bit the size of the cavity. These tiny changes in the size of the cavity can appear in the light if I lock my laser to the cavity. So the laser will follow the cavity. If the cavity moves, the laser frequency will also change. So this is also known as mode splitting. So you put one laser resonant with the atoms, the other laser far away from the atoms, then you put them, you locked the two lasers among them, and one of them is locked to the cavity. If the cavity changes size, one of the lasers is going to change size. So you will see a splitting in the resonance mode. So yeah, that's the way we're going to do it. Any other question? Bruna. Bruna has a question. She is coming forward. You can take that microphone.
Congrats on your beautiful work. I mean, my question is a little bit more conceptual, I think. I was going to ask, and it has to do with the second question Bruno did. So if I was to compare like these block oscillations you are doing, you are measuring with block oscillations from like a normal, from an electric field, like that could be done horizontally, right? For the electric field, you wouldn't have to have any other force besides the potential.
Yeah, you will need an electric field.
Yeah, but no other force in the opposite side to compensate for it. You wouldn't need that. The oscillations happens just with the presence of electric field, and
yeah. So the oscillation happen naturally because of, so the principle is you have a periodic potential, you have a equal space in potential, and you have how do you call that, wave function. So you have something that behaves as a wave inside of your periodic potential. Basically nothing happened, you just have like tunneling or whatever. But if this periodic potential and the wave function also is presented with a constant force, that means that your periodic potential moves a bit. It's like instead of being all periodic, you have the periodicity, but it moves a bit. Yeah, it changes a bit. So that means that the potential is higher in one side and lower in the other side. But in the lower side, you have the force. So basically, the wave function will go to the lower side until the force push the wave function, and it goes to the other side of the potential where the potential increase. So that's why you have the oscillation. You have in one side the force pushing, and the other side the potential increasing. So you have the oscillation is because of this.
So you could compare it with a classical case of a particle falling, and the particle would just, there is a potential, but it would just fall. But because it's a quantum, behaves like a wave, it has no zero probability of going back, up.
Yes, so what happened with us is that we have the matter wave, like really, really cold wave, and that means that you have a long, really long de Broglie wavelength. Yeah, so you have it really cold. Then it's gravity in action, so the cloud will decrease, will fall down. When it falls down, it also heat up, so it will experience heating, yeah? But heating means your wavelength decrease. When the wavelength decrease and is comparable to the periodicity of the periodic potential, you will suffer the cloud. The cloud will suffer. It's like the Raman beams. You will have a two-photon transition, so it will take one photon in one side of the lattice, the other one in the other side, and it will feel a push. It's not a push, actually. It's just a momentum superposition. So the momentum that the cloud winds going down will be back reflected in the lattice, and then all this moment that acquires going down will be reflected, and the cloud will go up.
Right. So you don't need to hold the cloud.
No.
But do you hold the cloud? Oh,
no.
Okay. So.
Oh, well, I hope I'm not holding the cloud, because if I hold the cloud, I will put a force, and I don't want to be interrupted by any force. So that's why we use far-off resonance light, because we don't want a force to hold the atoms. We don't want a friction or anything.
Okay. Thank you.
Thank you for your question.
Thank you very much, Talita. But I think it's time for the next
Yes.
participant. But thank you very much. The next poster. The next poster is about thermodynamic properties of interacting trapped Bose gases by Edmur Braga Martins. Se você quiser, você tem seu pôster o PDF, viu? É só você ir na desktop e você baixa para ele ficar maior.
Tá. Mas já vai aparecer ali, né?
Sim, fique à vontade. Ó. Aqui o microfone.
Boa tarde a todos. Eu sou o Edmur, aqui da Universidade de São Paulo. E o nosso trabalho é sobre propriedades termodinâmicas de gases de Bose armadilhados. O que tem se notado aí recentemente, né, nos últimos anos, é que nós não temos uma aproximação de modelos teóricos com medidas experimentais. E aí o nosso trabalho vem nesse sentido, né? Buscar caminhos, né, ou buscar modelos que aproximam a parte teórica com as medidas experimentais do laboratório. E aí, para isso, nós temos dois modelos, né, de abordagem, e com esses dois modelos, nós estudamos algumas quantidades termodinâmicas, né? Aqui no pôster nós apresentamos o potencial químico, a energia do sistema, né, a energia total do sistema, a capacidade térmica, a densidade de número, né, tanto para o condensado quanto para átomos térmicos, e a compressibilidade isotérmica, né. Aí lá no pôster, deixa eu ver aqui.
Já ajuda de novo.
Só para apresentar o pôster aqui.
Eu ajudo, pode deixar. Só minimizar aqui, ó.
Isso. Aí no pôster tem algumas... para descer o pôster aqui. Aí, então, aí aqui no pôster nós temos alguns resultados, né? O primeiro ali é o potencial químico, o segundo, na primeira linha, a energia do sistema, né? E depois nós temos a capacidade térmica. O quarto gráfico é a densidade de número, né? A curva azul é para o condensado, a cor vermelha é para os átomos térmicos. Depois nós temos a quinta curva, que é a compressibilidade isotérmica, né? E a comparação entre os modelos ali, né? A comparação entre os modelos nós colocamos para a capacidade térmica e para a compressibilidade isotérmica. E esses resultados foram todos obtidos para o gás interagente, né? Que é o gás que se encontra no laboratório. Tá? E, bem, é isso, né? E aí nós podemos agora ir para as perguntas.
Ali embaixo, Timur, página, pôster, página 2. Eu acho para
não,
você.
Oi?
Pode deixar.
Ah, tá.
Aí as perguntas, deixa eu descer lá para você. Eu vi bastante.
Aí nós temos aqui duas perguntas, né? A primeira fala assim, o quanto que o modelo é útil para se usar no laboratório. A pergunta era se o modelo é possível de usar o modelo no laboratório. A resposta é sim, né? Os dois modelos já foram construídos, né, estudados, justamente para os pesquisadores experimentais ter algo que você mede no laboratório e vai lá para os modelos e produz as grandezas, né? O experimentalista ele pode usar o modelo para produzir uma curva teórica, né? Depois ele vai lá no laboratório, ele faz as medidas deles, né? Ele pega aqueles parâmetros experimentais e volta no modelo e começa a pontuar ali, né, o gráfico dele com os pontinhos experimentais. Ele vai ver que os pontinhos experimentais está bem próximo da curva teórica, né? E todos os parâmetros do modelo podem ser obtidos no laboratório. E o modelo ele foi estudado por um range de valores, né? No caso aí nós trabalhamos com 10 mil átomos até 1 milhão de átomos. Nós podemos expandir a fronteira, nós podemos abaixar até para 1000 átomos, né? 100 átomos, se quiser, né? Pouquíssimos átomos. O modelo é robusto para isso. Também nós podemos ir lá para cima, né? Com 3 milhões de átomos, 5 milhões de átomos. O modelo suporta isso. Nós já testamos o modelo. A segunda pergunta é a respeito lá do potencial químico, né? Relacionada às funções de Bose, né? E a fugacidade. Na literatura, o que acontece é o seguinte: geralmente a fugacidade aparece lá só com o potencial químico, né? Exponencial de μ sobre kT. Só que esse potencial químico ele tem uma correção, né? Ele tem um shift ali. Na verdade, a rigor mesmo, né? Tem alguns papers que traz essa dedução para a gente. Na verdade é μ menos uma energia residual, né? Tudo isso sobre kT. Quando a gente considera essa energia residual, né, essa energia background, o que acontece? Aí não surge esses problemas que está na pergunta ali, né, de divergência, essas coisas aí. Então, e aí se a gente voltar aqui para o potencial químico, agora, para voltar aqui, qual que é?
Ela abinha aqui embaixo, essa aqui.
Ah, tá. Se nós voltarmos aqui para o potencial químico, né, que é aquele primeiro gráfico lá, considerando essa energia residual, né, lá na fugacidade, a gente não tem problema, né, de divergência, algo parecido, né? A gente vê lá que o potencial químico para temperaturas próximas de zero, né, ele é positivo, vai decaindo, né, chega uma hora que ele é zero e depois ele passa a ser negativo. Esse potencial químico ele é contínuo, né? Não tem problema de descontinuidade. E mais uma pergunta que foi feita em relação a um parâmetro, né, do potencial químico. Não, eu ia estar lá ainda.
Tudo bem. É com o mouse mesmo.
Tá, desculpa. Tá, agora
Vai com o mouse.
é que eu não estou acostumado com o notebook, então é isso. Bem, aqui no método, né, no modelo de CA, nós temos a primeira fórmula, né, que é potencial químico. Eu chamei ele de milinha, né, potencial químico. E lá no finalzinho da fórmula, de 1 menos T ao cubo, né, temperatura reduzida, né, temos lá um parâmetro alfa lá. Aquele parâmetro alfa que está ali apresentado no telão é uma contribuição nossa, né, porque isso aí até há pouco tempo não tinha na literatura. Esse parâmetro alfa corrige o problema de descontinuidade do potencial químico, né? Na década de 60, aquele potencial químico já era conhecido, né, pela aproximação autoconsistente de Popov. Só que quando surgiram os primeiros condensados experimentais, notou-se que era muito difícil trabalhar com o modelo autoconsistente de Popov, né? E aí tem outras limitações lá. E aí os pesquisadores da década de 90 buscaram então se trabalhar com o modelo de Hartree-Fock. Só que quando você trabalha com o modelo de Hartree-Fock, o potencial químico ele deixa de ser contínuo, comparado com o da década de 60. E aí agora nós conseguimos então, usando o modelo de Hartree-Fock, corrigir a descontinuidade do potencial químico, voltando a ser contínuo, porém com um modelo mais simples agora. Inclusive, possível de ser utilizado em laboratório, né? Então, acho que era mais ou menos isso as perguntas, né?
Ok.
Aí tem que ver se alguém tem mais perguntas para fazer.
Ok, please.
Pode falar em português mesmo,
Ok.
e aí ela vai. Desculpe, não entendi. Acho que está longe, eu não estou ouvindo. Os dois modelos? Tá, sim, desculpa. Sim. Tá.
Edmur, tenta ser mais breve, 1 minuto, por favor.
Tá.
Os próximos.
O primeiro modelo é o seguinte. A gente sabe que o sistema quântico ele é discretizado, né? Ele é discretizado. Mas você pode, assim, na teoria, você pode fazer uma aproximação assim da discretização, né, por integrais. Quando você passa para integrais, aí você consegue trabalhar analiticamente. E aí a busca do primeiro modelo, a modelo CA, em inglês é Continuum Approximation.
Mas
tá?
tem vários que
E esse Continuum Approximation é o que envolve integrais. A gente passa da configuração de séries para trabalhar com integrais. Aí é por isso que aquele rótulo ali, né? CA, Continuum Approximation, ou aproximação contínua. Oi? Não, tudo analítico. Os dois modelos são analíticos, tá? Só que, então, dos modelos, o primeiro modelo se trabalha com integrais, né? Você pode calcular tudo na mão, montar um modelo e fazer um intercâmbio com o laboratório. E aí o outro modelo aqui, GV é em inglês Global Variables, variáveis globais. E aí, só que esse outro modelo também ele é compatível com os experimentos. Só que esse modelo ele tem duas variáveis, ele tem duas grandezas termodinâmicas que é próprio do modelo, é peculiar ao modelo, que é o que a gente chama de parâmetro de pressão e volume harmônico, em que os produtos dessas duas variáveis dá a energia, mas não é pressão vezes volume, são duas grandezas peculiares, né? Tem vários trabalhos a respeito disso aí. Você multiplica uma grandeza pela outra, dá energia, tá? Aí teria que detalhar um pouco mais, teria que ter mais tempo para detalhar isso que eu estou falando.
Ok.
Tá? A gente pode chegar em T igual a zero, pode. Mas o que a gente tem notado é o seguinte: do ponto de vista experimental, a gente não tem T igual a zero, do ponto de vista experimental. Pode. Você pode estudar lá T igual a zero ou T próximo de zero, pode. Mas pode sim.
Okay. I think you have to go for the next participant. Thank you very much, Dimur.
Ok, obrigado.
Your Now you have Gustavo França with the poster Photon Statistics and Optical Control Considering the Phenomenal and Electromagnetic Induced Transparency within Atoms.
Hi everyone, my name is Gustavo. I am an undergrad student from the Federal University of São Carlos, the Sorocaba campus, not from here. And my work is about produce quantum light using an atom cavity system composed by a single free-level atom. Basically this. I just opened the poster. First of all, I just have to say this is a theoretical study, and I see that a lot of you are experimental physicists, so we're just creating problems that one day you have to solve. I'm sorry for that. Just to you understand what we're doing, this plot is just our result, and this is the second order coherence function, which is basically say to us, the statistics say to us if we are detecting these photons of the transmitted field from the cavity, one by one, or if we're detecting a bunch of photons each time. If you see there's a line, below this line we're detecting one by one, and above this line is bunch of photons each time. It's basically anti-bunching and bunching effect. And, or in other words, classical light and quantum light. And if you see here in the second valley, we have this region, this range when we can produce the quantum light, and if we change the detuning between the probe cavity and the field in the cavity, we get this range wider. And we're talking about the control field, which means when we change the detuning, we get a wider region where we can produce quantum light, which means it's getting easier to produce experimentally, because the control field is a classical field in our model, and is a external parameter, a controllable parameter. So this is what we're doing. And have two questions. I know the first one is just a compliment. Is very kind. Lucas Madeira asks, if I understand correctly, you studied n less than 3 system with 2 and 3 levels in order to include more levels or employ more atoms. Do you just need more computing time, or do you need a different approach? And I say we'll need both. If you see here the results, we expect when we add more atoms, when we employ more atoms, we expect to get a more wider region, to get more easier to produce the quantum light. And we're getting problems to do that. We already simulate for 2 and 3 atoms in the system, 3-level atoms in the cavity. And to 1 atom, it takes seconds to simulate. For 2, it's like some days. And for 3, it's weeks. And 4, it's, well, if we continue in this, we take months or years to simulate. It's not practicable. So we need more computational time, as you say, but we need a different approach too. And we're trying another numerical solutions to solve the system, and we expect to get more solutions soon, but we have both. We need more computation time, we need more memory, we need better computers too, or even a quantum computer, and a different approach and different numerical methods to get the solution for more atoms or atoms with more levels. I think it is. There is another question. Dalila?
You have three level atoms. Yeah. Which of the levels is resonant with the cavity, or both are resonant with the cavity?
Let me show the model. The cavity is resonant with the transition to 1 to 3, level 1 to 3.
From 1 to 3.
And we get the outer atoms effect and now the EIT phenomenon.
Wow, nice. Sorry.
This is
Okay, more questions? Oh, if not, thank you again, Gustavo. Your next participant will be Heitor da Silva, who is the poster A Study on Droplets of Light in Optical Nonlinear Media.
So, good afternoon, everyone, here in the auditorium, and also for those following on YouTube. So, good afternoon, everyone. So, my name is Heitor da Silva. I am a PG student at the Federal University of Rio Grande do Norte, under the supervision of Professor Tommaso Macri. And my PhD research is on quantum fluids of light. And today I'm going to talk about this work, which has been done in collaboration with Professor Robin Kaiser, whose title is Droplets of Light in Optical Nonlinear Media. So the idea here is to study propagation of light while it travels through a nonlinear media. And we know that under the paraxial regime, so this dynamics is essentially described by a nonlinear Schrödinger equation. So let's see. Okay, I have some problem here. Okay. Good. So basically, the description is given by this equation 1. And as you can see, this is very similar to the Gross-Pitevsky equation. If, for example, the second term on the right-hand side, the external potential, its role is played by the response of the medium, so the susceptibility. So in most cases, this response of the medium is nonlinear. So in this sense, for example, if you have a Kerr medium, so a Kerr nonlinearity, this becomes very similar to the Gross-Pitevsky equation. So in this sense, the motivation of this study is to investigate nonlinear phenomena already observed in BCs, but now using these quantum fluids of light. Okay. So in this specific work, the kind of physics we want to investigate, as I said, is quantum droplets. So in here, we have to consider at first a description for our nonlinear media. So we, the most direct description is that of a two-level system, but we also considered an alternative description, which is a four-level description. So let me show you here. So these essentially are the level descriptions for the nonlinear medium. And for this four-level system, essentially here, the excited states, we are supposing that they are degenerate. And also, all the decaying rates, they are equal, just to make the problem easier to treat. Okay, so let me skip to the questions. So I have a question, a first question, and then the second one is just a follow-up of the first, by Pedro Magnani. So first of all, thanks a lot for the questions. So what happens to the root mean square deviation and the excitation energy and chemical potential rate if you increase the incident power? Does the states still self-bound? Okay, so you know, I realized that the values that we are using for the incident power, they might be like too big values, because as you can see in the plots in the poster, the region for observing this briefing mode is very narrow. So if you use if you consider a smaller value for this incident power, what we can observe is that due to the constraint that you have in our variational approach, so the range of the values of the frequency detuning that we are allowed to explore will be smaller, but the window that we have for observing this briefing mode will be wider. So this was a good question, and well, and how does this increase of power may affect the briefing mode? So I think that just to complement, so we be able to have a wider window to observe this collective excitation. Yeah, so essentially if you increase this incident power, things become harder. So it is desirable to use a smaller incident power. And I think, so if there are other questions.
More questions? If not, I'd like to thank you, Eduardo. Thank you again.
And now we will be moving to our online participants. Our first participant will be David Ray. David, can you hear me?
Hello?
Hi, we can hear you.
Okay, sure. Well, cool. Thanks a lot. I'm very glad to be here. So, in our group, in the BC group at the LPL, we are working with a exotic shaped trap, and so basically we are confining our BC atom on the surface of a shell, and in order a question that we had asked ourselves was it possible to fill the whole bubble with ABC? And so we tried to find a way to compensate the gravity in order for the atoms to climb up along the all around the shell. And at first we thought that we would be losing all our atoms, because the maximum of potential of our trap is at the very bottom, and at the very top of the bubble, there is a zero coupling point where you can basically lose all the atoms. So, yes, yes, so that was pretty much, and in order to compensate the gravity, we just had to increase the magnetic gradient, and then the atom climbs along the to the top of the trap. And what we've seen is that things didn't happen as we expected. We managed to compensate the gravity, but we had to increase more so we had to increase less the gradient than what we first thought. And also, the atoms had not the behavior we thought. They were first climbing, and then they were kind of maintained at a given altitude, as you can see in the experimental results part of the poster. And in order to have the most precise altitudes, you had to take beyond rotating waves approximation term in our in the simulation of our trap, in order to be as precise as possible. So there had been a question of Leonardo, and so the question was, your gravity compensation is performed by a potential that depends on the atomic mass of the gas. If you have a mixture of two species, do you think you could cancel the gravity for both species simultaneously? So first of all, thank you for the question. A kind of long form, a kind of very short answer might be, it can be, but it might be very difficult for us to trap two different species inside our trap at the same time. And for me to give a kind of hand-wavy argument, like, you know, it would be, so the idea would be that first, if you want to trap two different species, you would have to get two different RF fields. And if you get two different RF fields, you will have basically two shells for each atoms. And by doing this, you can tune the RF fields in order to trap both species on one common shells. And that would be a kind of basic idea in order to get both of your part of both of the species in one of the four bubbles. And then by doing this, you would have to then by doing this, if you want to compensate gravity for both species, and by doing, like, you know, very simple math, you can see that the only way for you to get the gravity compensation for both species would be to have so the ratio m1 over m2 being equal to the ratio of magnetic momentum mu1 over mu2. And so that's a kind of quite rigid condition, and I haven't looked for an answer in order to have like a kind of practical example, and if it is possible with atoms that you can trap on the lab. But yeah, that would be my question, my answer. It's maybe theoretically possible if you can satisfy this condition. Is there some other questions?
Thank you for your answer, David. Let's thank David. And now we move on to our next speaker, Eduardo Padilla Castillo.
Hi.
Hi,
Can you hear me?
Can you hear me?
Yes, I can hear you. You can hear me?
Yes.
Perfect. Well, we developed an optical dipole trap, which is really, really flexible, really, really moldable, and that allows. And it was using the same AOM that we use for evaporative QLF. It was not necessary a DMD. It was not necessary another expensive electro-optic element, and what else? And basically, we can change, for example, the volume and the size of the trap also, and also that allows us to create some experiments, thermodynamic experiments. We are planning to do thermodynamic experiments to really change the volume variable instead of and also the temperature. For example, let me try something here. I'm going to choose my virtual. Okay, a moment. For example, we can create a double well trap. Maybe you can see in my video, and we can pass from a single trap to a double trap, and we can change the size of this of we can check the distance between this double well, and this is really useful for example do wave interferometry between these two Bose-Einstein condensate and see an interference pattern. What else we can do with this potential? For example, we can also, for example, we can change the geometry. We can begin with a really Shiger-shaped trap and then go to somehow a pancake trap. So this is really useful also. And what else? And for example, we design an experiment, for example, then instead of changing the temperature, we change the volume to get a Bose-Einstein condensate. So this is what you are looking here. Instead of change the temperature, we decide to keep, for example, 50 nanokelvin, and then we compress the trap, and then we get a transition phase. So this is instead of lower the temperature, we decrease the volume somehow, and we saw this Bose-Einstein condensation. And also, for example, for one project that Diego going to show, it is the Faraday wave. For create this Faraday wave pattern, we need that the trap is really symmetric or really radial symmetric. So for that, we can use this technique because our trap it was slightly not symmetric. So with this technique, we do really a Shiger-shaped trap. And well, that's all. If you have some questions, and I think there's one in the web page. Can you read it? Because maybe here. Very good poster. Did you calculate the global pressure when you change the volume through the transition and any thermodynamic susceptibility? No yet. This is one of the future projects that we think. Some of the limitants to do this is it's really right now we are working with lithium-6, so this is somehow strongly interact. So for do that we need a really weakly interact we can work with the lithium-7 for do that, but we already don't have that, and the tool is there, so at some point we can use it, and that's the thing. There's some questions in the auditorium that you want to make?
Thank you, Eduardo. If someone has a question, ask that you email that to Eduardo. So let's thank Eduardo.
Okay. Thank you very much.
And now, Andrés Gutierrez.
Yes, hello.
Hi, we can hear you.
Can you see me now?
Yes, now we see you.
Perfect. Well, thank you very much for the opportunity of participating in this school. My name is Andrés Gutierrez, and I did my undergraduate thesis under the direction of Professor Jorge Seman at the Institute of Physics. My project basically consisted of an RF system, which I built and designed, and then tested on our experiment to excite transitions between the three lowest hyperfine levels in the lithium-6 atom. I have two questions in the site. Diego Hernandez asks, what are the limitations of this setup? The main limitation, as you can see from my results, is in the efficiency of the antenna itself. The wavelength needed to excite the transitions in the magnetic fields that we're using is of about 4 meters, and the antenna, by the constrictions of the experiment, is only around 6 centimeters in diameter, so it is inherently inefficient. But also, by the Rabi frequency that we are measuring right now, we see that the atoms in the sample are probably not receiving the full power that they should. So that's mostly a physical limitation, but also in terms of the hardware, the limitation is that we can only use one antenna at a time. This means that if we want to do the 1-2 transition, we must use one setup, and if we want to do the 2-3 transition, we must change physically the antenna. Because each has its own tuning circuit, each needs to be amplified, and so on. So when we want to perform different transitions, we must change it. This leads us to the second question that was asked by Juan Carlos Obeso. He says that what improvements are we going to make? What optimizations are we planning to do in the experiment? And well, with the same idea, we're currently working on how to improve the power delivered by the setup to the atomic cloud. And we will do that by changing the geometry of the antenna so that we might alter the shape of the field, and then we can improve the power in the atomic sample. We hope that this will allow us to raise the Rabi frequency at least by an order of magnitude. And we are also, of course, working on an electronic circuit that will allow us to change between antennas without having to physically alter the setup. This should allow us to easily use schemes such as that will maybe transfer the atoms from the state 1, then 2, and then 3 very seamlessly. I hope this answers your questions. And please, if you have any other questions, you can ask them to me now.
Well, thank you, Andrés. Let's thank him.
Thank you.
And now we have Bárbara Ribeiro.
Hi.
Hi.
Okay. I will present the project of my PhD that was to construct a model for an opioid tree. The focus of this project is to study the entanglement between the beams of the parametric optical oscillator Chi3. A parametric optical oscillator Chi3 consists of an optical cavity with a gain medium inside it. Then we pump this gain medium and we generate a forward mixing process. Then the generated beams, we call them signal and idler. And we will have entanglement between pump, signal, and idler. And I use the first we did a model to study the mean fields, and we get the first two curves in this poster. In the case of a triple resonant OPO, no, sorry, first in the case of a double resonant OPO, when the pump do just a single pass, we have a linear behavior, and in the case of a triple resonant OPO, we have a parabolic-like shape. And then we use those data to feed our quantum model, where we study the covariance matrix, and then we use the PPT criterion to characterize entanglement. Then in my poster, I highlight the principal characteristics of disentanglement. We find first we study just the symmetric part, just the symmetric base, and we find that we have a stronger entanglement between signal and idler, and we also have entanglement in the pump, but it's a little bit less. Then when we include the antisymmetric bases and study the entanglement, we find that signal and idler didn't behave very different from the behavior you have when you study just the symmetric part, but pump shows more entanglement. Then the conclusion is that in the case of pump, you also need to study the antisymmetric bases to see more correlations that it have with the other beams. I don't have questions in the box, but
You do have one
I'm
question.
open to answer questions now.
You do have a question. It's what would be a simple quantum computation that could be done with the system?
Well, the idea is that you have many protocols in quantum computation, like teletransport and others, that needs entangled beams. So the idea is to use disentanglement to, for example, to use that in a teletransport protocol.
Barbara, can you hear me?
Yes, you hear me?
Yes, now we can. Yeah. So you're saying
okay,
teletransport.
you hear me before when
Yes,
I answer
yes,
the
we do.
question?
Yes.
Okay.
So let's thank Barbara for her presentation and answering the question.
Thank you.
Thank you, Barbara. Now, Ciro Martins.
Yes, can you hear me?
Yes.
Okay, so thank you very much for the organizers to taking part in this school and for the opportunity to present my work. My work is not exactly on quantum fluids, it's about classical fluids, but we apply a new technique which hopefully can be applied also to some formulations of, for example, superfluids. The problem we address is the blow-up problem in the three-dimensional incompressible water equations. So it's a long-standing problem, and it's completely open about finite time singularities in these equations in this system, and it's completely related to the development of turbulence. And there are several studies, for example, using direct numerical simulations around this problem, but most of them are not fully conclusive, especially because the resolution available on the computers, the computational power we have today, cannot reach the resolution to study this problem. So we developed a new technique because if we want new results, we need new techniques. So we developed a new technique to study this problem, which is essentially to take the equations in Fourier space, but instead of using regular grids in Fourier space, which is the usual procedure in direct numerical simulations, we performed all the simulations in a logarithmic lattice, which are the wave vectors are distributed in a logarithmic way. And we do so because with this in mind, we can perform very, very fine simulations with only a few nodes. So we can reach very, very fine scales. And by using this technique, we show numerically a clear evidence of blow up in this system, a finite time singularity, which is characterized as a chaotic blow up in a renormalized system. Well, this is a numerical integration, and the question left by Alex Andreatti concerns exactly about the evolution in time. So he says, as I understood, even after this logarithmic grid transformation in Fourier space, you need to propagate the equation in time. Yes, it is right. The Fourier transformation is applied on space variables, so we still have time evolution. And he asks, which algorithm is used? Is it an ordinary differential equation, right? Yes. We have a partial differential equation, a nonlinear partial differential equation in physical space, but we can think about periodic domains. So once we take this equation to Fourier space, it becomes an infinite dimensional ordinary differential equation, but still evolving in time. So we have used a very simple Runge-Kutta of fourth order to evolve in time. And it's adaptive in time and spatial resolution. And we use adaptive time space by comparing the fourth order method with the fifth order method. So it's an adaptation of Runge-Kutta-Fjellberg adaptive scheme for time marching. So this is essentially my work, and there is a reference in the poster for more details. And of course, you can write me emails if you have more questions. Thank you very much.
Thank you, Ciro. Let's thank him. Our next speaker is Diego Hernandez Rajkov.
Yes, can you hear me?
Yes.
Okay. So the work I present here is about the observation and characterization of Faraday waves in strongly interacting superfluids. So the work that I present is done in a lithium-6 fermionic lithium superfluids in the BC side of the Feshbach resonance, that is between the two lowest hyperfine states of lithium-6. And what we did to excite these Faraday waves is to excite collective mode by parametrically exciting or parametrically changing the radial confinement of the cigar shape of the cigar trap, where we have the superfluid. And if one can see that when we parametrically excite the radial confinement, we see the appearance of a spatial pattern with a temporal dependence, meaning that we see a spatial pattern that oscillates in time, appearing and disappearing. And these are the so-called Faraday waves. So we try to study these Faraday waves as a function of the interaction, mainly going from a weakly interacting molecular Bose-Einstein condensate to a stronger interacting BEC, and eventually the goal was to study the Faraday waves in the unitary regime, where the scattering length of the system goes to infinity. No? So I have one question from Patricia. I have three questions. The first one is, in figure 3, you say that the atomic cloud is trapped in an optical magnetic potential, and for that reason you can decouple the modulation between the transverse and axial frequency. How is it so? In what percentage do you modulate the axial frequency when modulating the transverse one? So our trap configuration is given by first an optical dipole trap, a single beam ODT, in addition to a confinement due to a magnetic curvature. In our case, we have that the radial confinement of the cloud is given by the trapping of the optical dipole trap, and the axial, the long direction, is trapped by the magnetic curvature of the phase-back coils of the magnetic field. So in practice, I think the magnetic curvature basically is then one order of magnitude higher than the optical dipole frequency along the axial direction, while in the radial confinement, the optical dipole trap is at least 2 orders of magnitude bigger than the radial confinement of the magnetic the radial confinement of the magnetic curvature. So basically, we can change by a small fraction. In our case, we modulated up to 10% the radial confinement. That is basically, we don't change the axial one by at least 1 order of magnitude less. No? The second question is, the image in figure 4 is a single shot or integrated images? I ask this because in the absence of a sharp border in the axial direction, I would expect the position of the maximum minimum of the Faraday pattern to move with respect to the to different experimental runs. Do you see this effect? If so, do you correct the integrated images for that? So the image I show in figure 4 is an average over 10 different experimental runs.
Diego, can you hear us? Diego? Okay, so I'll move on to the next speaker, and then if he reconnects, we can resume our discussion. Next, we have Jacob Dobos.
Hello, everyone.
Hi, Jacob.
So I hope you can hear me.
Yes, we can hear.
Okay. So in my work, can you show my poster on the page?
Yeah, you can go ahead.
Okay, thank you. So in my work, I'm planning to build, or actually I built, and I'm planning to implement that further, an interferometer. And this is a heterodyne interferometer, which means that it detects the phase not between two beams of light, but between coming from the same laser, but between two beams of light that have a little different frequency. And this different frequency is of course generated by acousto-optic modulator, as often in AMO physics. And the reason to build such an interferometer is mainly to speed up the spectroscopic measurements, but we have some other ideas on what to use it further. So the main idea is that in phase, there's encoded some information about the interaction between the atoms and the light. And for that reason, we usually make absorption photos. But those absorption photos are heating up the atomic sample. And there is an idea to use the phase of the light, not the energy as used in absorption photos, to extract some information about the cloud. And as you can see in this, in those small equations in the phase section, the absorption of the atomic sample falls faster, because it falls like 1 over the tuning squared, than the change in phase. So the change in phase is just 1 over the tuning. And for this reason, there is a regime that we can use, let's say, as a work point of our interferometer, in which the absorption of the sample is negligible, but still there is some phase shift. Okay, the next part is the interferometer setup, and I will leave that for now because I will come back to here when answering the comments from the site. And then there is a nice plot. I guess, in my opinion, it's nice at least because it looks exactly like the plot that you can see in the books for some introductory courses to light matter interaction. So this is just the phase and absorption, and actually this is just the index of refraction. So this is some calibration measurement that I've taken with the interferometer and show that it works the way I intended. And then there are those two plots that I presented with destructive and non-destructive approach. So the destructive approach is just the absorption of the laser going through the sample. And it shows that in one case where I was detuned closely by 3 megahertz, there was some absorption seen and some dynamics of the cloud was measured. Actually, this was loading of the MOT. Sorry, it was releasing the cloud from gray optical molasses. So the intensity of light grew because the intensity of the light grew because the density of the atomic cloud decreased, and less light was absorbed. And in the second regime where I was detuned further, there was no absorption observed. However, when I used the interferometer to measure the phase, then in both cases there was something measured. So this is the idea, not to use absorption and to use phase as a determination of what happens with the dynamics of the cloud. And now, if I can go to the questions from the website, because I guess it's an extension of what I said now. So the first question, it's a little long, so I guess that I will only read the questions. So is it possible to use such interferometer to measure your cloud size or other parameters such as optical density, for example? So the optical density is actually the thing that the interferometer measures, because this phase of light that interacts with atoms is proportional to the density of the probe. So that's the main parameter that we get. And then we can, of course, convert that to the number of atoms if we want to. And then if we could measure the size of the cloud. So this thing is a little bit more complicated, because usually I focus my my lights coming from the interferometer on the atomic sample. So it means that I measure only a fraction of the whole cloud. And yeah, I don't measure the size. So I guess that to measure a size, you would have to expand the beam, but still, in the end, what you get is just one number, right? Because it's measured on a photodiode, and you measure just one number, just the phase. So I guess that it would be more difficult, but of course, you can do something like, let's say, a workaround of that, and you can measure the dynamics in the time of the experiment using the interferometer, but then in the end make an absorption photo just at the end, and from this absorption photo and known dynamics through time, maybe somehow recalculate back what happened to the cloud. So maybe that would be an idea, but I never tried that, don't know how accurate that is. Okay, and the next question also, even though the heating of the sample may be negligible, is this limited by the type of sample you have? For instance, a colder sample such as ODT operating at microkelvins would suffer more from this heating than MOT. So yeah, that's true. MOT is firstly not as cold as ODT, and the second thing is that MOT is constantly reloading, because if you have some vapor, some leftover vapor pressure, then it is reloading the MOT of the things that were absorbed in the MOT. We don't have that in ODT because it's, yeah, there is nothing more than ODT. And yeah, that would be a problem. But however, I don't have any idea how to measure that, but from my understanding of the theory, if you go with the tuning from the transition in the regime that there is no absorption, but still there is some phase, it means that there is no absorption of the photons in the terms of the changing of the internal state of atoms. I mean, changing the energy levels, but there is some change in the wave function by the means that the atoms have induced polarization. So this, it's not probably good to say that we are not interacting at all, because still it is light matter interaction theory, but it gives us an opportunity not to change the energy state, but to just polarize the atoms. So something is changed. The main change is in the density of charge distribution, but not in the internal states of atoms. So in this means this is non-destructive. And of course, I'm using such low powers as nanowatts, so that, yeah, even in the ODT, it should work. So that's the thing that I'm actually measuring right now and trying to get. The ODT. Okay, and such heating would still be negligible since there is little absorption. So yeah, that was the answer. So two things: the tuned beam, and then so that only the polarization is induced in the atoms, not the absorption, and then of course low light intensity, so that the absorption is negligible in the terms of low probability. Okay, and the second question, I have a question regarding the non-destructive approach, that it seems to me an inverse problem, measurement of phase. So, which is quite difficult numerically depending upon the one's approach. So I was just curious to know how I solved that. So with the phase measurement, actually, I didn't put that in the poster because I thought that it's, you know, less interesting than physics. But I use analog devices so that I can to analyze I use electronic devices to analyze the signal. So I don't reconstruct the phase from the signal directly from the photodiode, but I use IQ demodulators to demodulate the signal. So from the interferometer, as you can see in the scheme, there are two arms. One of them is called ref, which is reference arm, and the second is called probe. And in the reference arm, I get from that something like a local oscillator for the electronics. And then when I have this probing arm is shifted by the interaction with atoms, and the bit node coming from the probing arm then is demodulated with respect to the reference arm. And that's the algorithm, let's say, that I'm using. So I'm using electronic components to analyze the signal like in real time. Okay, and those were the questions from the website. Yeah, so thank you for that, and I don't know, maybe there is something from the audience.
Thank you for your answers. Let's thank Jacob. Our next speaker would be James Nettersheim, but I understand there was some problem. Somebody's feeling for him.
Exactly, it's me. I'm Julian. Hi.
Hi, can you speak up?
Hi, I'm Julian, and I will substitute Jens since he can't attend today.
Yeah, go ahead, please.
So, as I said, I'm Julian, and in our experiment, we can immerse up to 10 cesium atoms into an ultra-cold rubidium gas. And in the project I want to explain to you, we realized an Otto engine with these cesium atoms as the working medium and the rubidium cloud as the heat bath. And I will now go to the questions because they were mainly about our experimental procedure. And I think these were good questions because it was asked how our experimental procedure is and if we do this Otto cycle with one atom or with multiple atoms. So we do it, all these measurements we're doing with the same atoms from beginning to the end. And in the very first beginning, we trap and cool about 10,000 rubidium atoms in an optical dipole trap. Before they were cooled with two MOTs, with a 2D MOT, and then these atoms are loaded into a 3D MOT, and from there into this dipole trap. And afterwards, when the rubidium atoms are cooled down to a few hundred nanokelvins, we have another MOT for our cesium atoms. This prepares 8 to 12 cesium atoms, and then they are loaded as well into our dipole trap. And there they are further cooled down by degenerate Raman sidebond cooling, since you can't evaporatively cool single atoms. After they are cooled down and pumped to one Siemens state, they are transported into our rubidium cloud with an optical lattice, which is tuned to a magic wavelength, so it does not affect our rubidium. So rubidium stays where it is and is not heated, but our cesium atoms are transported into the rubidium cloud. And in this cloud, they perform inelastic spin exchange collisions between cesium and rubidium. And by this, they change their Siemens state they change their Siemens state. And these collisions, they realize our heat engine, since heat is exchanged between the bath of rubidium and the working medium, which is cesium. Initially, during this interaction, the rubidium atoms are in the high spin state, while cesium is in the low spin state. All these 12 cesium atoms are in the same low spin state. And the magnetic field, which is our control parameter, which would be the volume in a classical heat engine, is at its high value. So it's we only have exoenergetic heat transfer from the rubidium bath to the cesium working medium, which is realized through the Siemens states, the quasi-spin states. And the next part of our Otto cycle is then initiated by a magnetic field ramp to a lower magnetic field, which would be the compression in a usual Otto engine, in a classical Otto engine, and a microwave pulse then flips the rubidium atoms into their low spin state, which is then the colder bath in a classical engine. Then we only have this heat exchange which is endoenergetic. So all the heat is going from cesium to the bath back, but since the magnetic field is lower and the Siemens splitting is lower, less heat is brought back to the bath that then went from the bath to the cesium atoms in the first step. And to fulfill the cycle in the end, the magnetic field is ramped back to its original high magnetic field value, and the rubidium state is changed again with a microwave pulse. And in the end, which may ask one of the question, we state selectively image all the cesium atoms by fluorescence imaging, and this is also on the poster. There you can see on the left there are pictures of single cesium atoms after the interaction with rubidium, and you can see there are, I think, 7 atoms left in the end, which are in some state. And on the right you can see this full counting statistics of all 7 Siemens states in the time evolution after, and the time evolution is realized by interacting and stopping the interaction with rubidium.
Can you hear me? Oh, okay.
Yes, I can hear you.
Yeah. Thank you for your time and your explanations.
Thank you.
Next, we have Juan Obeso.
Yes, I'm here.
Hi.
Hello everyone.
Yeah, please go ahead.
Thank you. Well, the poster is about 3 functions: pair wave function, density correlation function between opposite spins and parallel spins of 3-dimensional Fermi gas with equal population of spins. The main results we show are the large distance behavior of the 3 functions. And we found that they have an exponential decay behavior and an oscillatory behavior also. We associated the exponential decay with binding properties that can be calculated within the mean field model. I will answer the 2 questions that I have on the web page. The first one is from Eduardo Padilla. What can you tell us of the structure that looks periodic in the graphs of figure 2? And there is some physics related there. This fluctuation have some characteristic frequency. Yes, thank you for the question. On the BCS side, these oscillations are associated to the presence of a sharp Fermi surface. And as we move to the BEC side, the Fermi surface is smeared, or it vanishes. And well, we associate that distribution of particles on the wave vector space to be a physical explanation of how the oscillations are on the space representation of the correlation functions. Well, also on the BCS side, the frequency is given by the Fermi wave number, which is in accordance with a non-interacting gas. The second question is, is from Lucas Madeira. How do you expect these functions to change in polarized systems? For example, adding a spin-up particle and looking at the BCS and BEC limits. and unitarity? Well, that's a very nice question. Well, I'm also interested in that question, and I'm working a little bit on it. Well, first, we will have to study four density-density correlation functions. The ones between up-up, down-down spins, up-down, and down-up spins. Because in the polarized system, they are not, well, we cannot equal the up-up with the down-down. Then what we would expect to change is that at the mean field level, I would expect them to exhibit different exponential decays, but associated to a type of threshold energy to dissociate pairs, but it will depend on the polarization and the oscillations. I would expect them to be dependent on the Fermi wave number, but of each species, of the up or of the down. But I cannot comment more about it. That's a very, very nice question. And those are all the questions from the web page.
Yeah.
And I can answer more questions from the auditorium.
No, thank you for your answers. Well, let's thank him.
Okay.
Next, we have Marie Melody Vollard.
Hello.
Hello.
Yes, my name is Melody. I am a PhD student at Aalto University, which is in Helsinki, in Finland. So my poster is about some work I've been doing as part of my PhD. And in my group, we are working with superfluid helium-3, which is not really talked much about in this school, but it's definitely a quantum fluid. And in this work, very briefly, then we use, we alter the confinement where we keep the helium-3, which creates a new phase that we call the polar phase. And then in this particular phase, we did some work to show that the Anderson theorem can be extended to the polar phase of helium-3. And the Anderson theorem is normally used to, in the case of classic superconductors, so S-pairing Cooper pairs, to explain why they are, why the properties of superconductors are invariant to the addition of sorry, the time difference means that it's very hard, of defects. And so we found that this theorem can be extended to superfluid helium-3. And I have seen one question that was asked by Pedro regarding a figure, one of our results. So he's saying, could you please explain a bit more why your proportionality constant differs from the expected for high pressures? And so thank you for the question. And this is not the first time I get this question. And the reason why there is no explanation provided in the poster is that we simply do not know. So this is new physics that we found. So we tried to do some correction to our calculation which is shown in the graph, but the equations that we knew of still were not enough to explain our actual results. So we have some more competent people than me, some series that are currently working on this particular question. And so the answer, unfortunately, will have to wait a bit more for us to fully understand why the pressure affects so much this proportionality constant.
Well, thank you, Melody, especially given the time difference. We really appreciate that. Let's
yeah. Thank you.
Now, is Diego back to the call? He was talking about Faraday waves, but then his connection dropped. Okay, I don't think so. So we are going back to the presential speakers. Monica, please.
Okay, we still have two participants to present today. I would like to call Leandro Machado, and his work will be quantifying the non-equilibrium in rubidium-87 Bose-Einstein condensates trapped in harmonic potentials.
Hello guys, good afternoon everyone. I think we are late, right? Yeah, okay, in this case I will be fast, so sorry. The main idea of this work is a proposal of a way to quantify the non-equilibrium in Bose-Einstein condensate, and based on your density profile. When we talk about Bose-Einstein condensates, we know that the density profile is a parabolic curve given by the Thomas Fermi curvature, and as the cloud has the thermal part too, we have the Maxwell-Boltzmann distribution, and then a Gaussian curve, and based this, we define a new parameter that we will compare the Gaussian, the real profile of the excitated cloud to your fit, to that's bimodal fit, and then we can increasing the excitation amplitude, the delta shows that how far we are to the equilibrium, and that is the idea of the work. Okay, that's the question. I think okay. Inácio asks, have you calculated non-equilibrium parameter using another fitting? Well, the answer is no. But based on old works, we know that when you increase the excitation amplitude, the density profile of the Gaussian become a exponential profile, and then it's a test that we can do. And the last question is, how do the curves change using another fitting? So I think the delta parameter compare how much we are far from equilibrium, and then using another fit, I expect that the delta decrease because we are comparing with another fit, and I think that's it. Thank you.
Okay, is there more questions? Okay, thank you very much, Leandro. Okay, now you have the poster Stability of Bose-Einstein Condensates Mixtures on the Spherical Shell by Leonardo Brito da Silva. Okay, go on, Leonardo.
Okay. Good evening, everyone. First of all, I thank the organizing commission for the opportunity. I thank you. So I will present. Sorry. So I present a brief summary of my poster. Recently, I can see some experiments have been performed at NASA Cold Atom Laboratory. In microgravity environments, it's possible to build Bose-Einstein condensates in bubble shells. So in this context, we study how can be the stability of mixture of Bose-Einstein condensates on the shell surface, a hollow sphere. To carry out this study, we make a Bogoliubov-Degen's study to predict the stability diagram. Here is the case where we have the condensates with charge vorticity, one species with positive vorticity, and another species with negative vorticity. So you build in figure 3 a stability diagram for this case. This is a semi-analytical prediction, and we check our result by a dynamic simulation. And we find the stability diagram, a specific angular mode makes the system unstable, and we can check our result when we see the system to be broken by this mode. So the figure 4, we see a case where the mode, azimuthal mode equals 2, breaks the system in 2 pieces. This is a way to check our results. In this way we can study the stability of vortex on the surface of the sphere, and specifically the system of mixture of Bose-Einstein condensates. Let me see the questions. So, there is a question from Pedro. Hi. And the first question, about the small repulsive interspecies leading to a collapse and revival periodic regime for the condensate. Does this only happens in microgravity environments? No. The microgravity environment is needed to get the bubble shell, and not to get the collapse and revival phenomenon. This phenomenon can be seen in other contexts, like optical lattices, cold atom in optical lattices. the papers from Emmanuel Bloch, we can see this phenomenon. It's another context, but it's happening on Earth, so the microgravity environment is not needed. The microgravity environment is needed to get the bubble shells, especially spherical shells or ellipsoidal shells. How does the gravity affect the frequency of this behavior? I don't know. Every single term we insert in the Hamiltonian and the Gross-Pitarevsky equations will affect the stability diagram, but I don't know how it's happened. It has anything to do with the previous phrase at the conclusion. Angular unstable mode implies the number of pieces the condensates will be broken into. I don't think it's an effect of the gravity. There are angular modes in the small amplitude oscillations around the stationary states, and these modes sometimes breaks the system, makes the system unstable, but I don't think it's an effect of the gravity. So, thank you for your question. Any more questions?
No more questions? Okay, let's thank Leonardo again.
Thanks.
Our last participant, Luis Gustavo Mendonca Tenorio. Please, Gustavo.
So, okay, my name is Gustavo. I'm a master's student from ITA, and today I want to present some of our preliminary results of our group about excitons in heterostructures, van der Waals heterostructures, composed of TMDs. So what we did is just to build an effective theory of a two-layered system with three dielectric regions, solve the Poisson equation, and build a Schrödinger equation for this effective potential, and try to understand some of the properties of those two body bound states that we call excitons. So essentially the crux of the paper is the method that we are employing, which is a Chebyshev polynomial expansion that leads to a semi-analytical treatment that we can use to solve for the effects of the environment, which is the dielectrics and the separation between layers. And these are some of our results with respect to the energies and the wave functions of different states. And I guess I have one question, so take a look. So it's by Lucas, so let's take a look at you. Okay. Is it possible to draw a parallel between exciton Bose-Einstein condensations and the BCS theory of superconductivity? So it is possible, and recently we have some studies about how they form in a double-layered TMD with HBN, boron nitride, between the layers. And so when we have these interlayer excitons, so we have this bound states of electrons and holes, and they behave under certain conditions, similarly to a degenerate Bose gas. So we can perform the same theory
But as we know from relatively simple results, the effective mass of the exciton is smaller than the electron mass. So we should expect a higher temperature, which kind of happens. It's the temperature, the usual critical temperature is near the high TC, roughly 100 K. So it's a possible avenue to study Bose condensation, and the main issue with studying such systems is that the exciton lifetime is really short. So by having a short lifetime, it's kind of hard to maintain one. Now we can try, this is our best efforts to understand the lifetime of the exciton, and we are trying to do so, but it will come in a later study. Okay?
Okay, Luis, you have more questions? No more? Okay, let's thank Luis Gustavo again.
Thank everyone.
And now we will close this section. I think Lucas has some information for the on-site participants. Please waiting. Okay, thank you very much.